Hello, friends. I am Abhishek Datta, an assistant professor at the School of Engineering at the University of Connecticut. I'd like to present my paper titled Predicting Drug Mechanics by Deep Learning on Gene and Cell Activities. The challenge here, as we all know, is that the process of drug development is lengthy, laborious, and cost-intensive. Now, the drug development process itself can be briefly summarized as follows. In the first phase, that is the preclinical studies, there is a search for active substances, followed by toxicological effect studies, and finally, industrial authorization. This alone takes around 5 years. This is followed by the second phase, which is the clinical studies. The first phase is conducted over around 50 subjects, then the second over 100, and the third over around 20,000 to 50,000 patients. And only if the results are positive, then a new drug application authorization process is started. And beyond that, a continuous comparative studies is performed, which is also called phase 4. And this entire clinical studies takes roughly 10 years. So in total, the process consumes 15 years for a single drug, costing over millions of dollars. So my approach in this paper is the following. In order to shorten this development process and come up with some meaningful drug mechanics, which is seldom known, what I propose is the following. I collect around 100 cell lines, and these are mixed with known drug molecules, that is the drug molecules for which the mechanism of actions are already known. Now, when one particular drug molecule is mixed with these 100 cell lines, the resulting gene expression change and the cell viability change are noted. Now, this data set can be used to train a deep learning model. So the input of this deep learning network are the cell viabilities and the gene expressions. And the output of this deep learning model is the drug mechanism of action. So once this is trained over sufficiently large number of drug molecules, for example, around 27,000 in this case, then once there is a new drug molecule, then the process is just to apply the new drug molecule on the same 100 cell lines, note the change in gene expressions and cell viability, feed in to the trained neural network, and note the prediction, that is the new mechanism of actions. Well, with this approach, I want to now systematically look at what happens to the distribution of the cell activities and the gene expressions on application of drugs. So here I'm noting two kinds of mechanism of actions. One is an inhibitor and the other is an antagonist. So as you can see, for the inhibitor, there is a considerable change in the distribution for gene number 400, 401, and 402. And the same can be noted for cell 50, 51, and 52. However, the distribution shift is marginal for antagonist. But this also proves that these gene and cell activities can be used as markers for the mechanism of action. However, the set of 100 cell viabilities and 772 gene expressions constitute a very large feature vector of 872. So I would like to see if that can be compressed. So first I conduct a principal component analysis on the gene expressions. And the result shows that only one dimension can explain 25% of the variance. And if I would have to take just 6 dimensions from the 772, it would already have explained 50% of the variance. And the same can be said for the cell viabilities, which is even stronger, that just 1 dimension of the principal component of the cell viabilities can explain more than 80% of its variance. So to explain 90% of the variability, I could reduce the feature set from 872 to just 355. You can see in the factor maps that the first 2 dimensions account for much of the variability. And for the cell, you can see it's the dimension 1 that accounts for a lot of the variability. So next is the cluster. Now that we have the lower dimensional space that the principal component analysis has been performed, I want to show that the data already forms certain clusters. So if you can see the left figure, this is the gene expression principal components, that is the first and the second dimensions. Now I have plotted a lot of data points here corresponding to the various drugs. And the data points now correspond to 0, 1, 2, 3, 4, 5, and 7 mechanisms of actions. Meaning the pink data points corresponds to those gene expressions that have a net total of 7 mechanisms of actions. There can be 200 mechanisms of actions. So the same thing I do with the cell viabilities. So I plot the data for the first 2 dimensions of the reduced space for 0, 1, 2, 3, 4, 5, and 7 net mechanisms of actions. And you can already see that this data forms nice clusters. So this gives an impetus to why a deep learning could actually predict these mechanisms of actions. So now to the deep learning. So this is the meat of this paper. So this shows the entire life cycle of the problem. So I start with 100 cell viabilities and 772 gene expressions corresponding to each drug being given. Now, I have around 28,000 such drugs. So apart from them, there are 3 categorical variables. So that is the drug dosage, which can be low or high. The type of the drug can be control or the drug itself. And the duration can be 1, 2, or 3 days. So these 3 parameters, I do integer coding of that. And the 100 plus 772 features, like I did before, I did a principal component analysis and I reduced it to 355. So 355 plus 3 becomes 358 feature vectors, which is the input to this deep learning model. Then I design a first hidden layer which has 256 neurons. Then the activation function I choose is a leaky rectified linear unit. Then I do batch normalization and a dropout regularization of 0.2. Then I have another dense, fully connected layer of 256 neurons, and I again perform a leaky rectified linear unit activation alongside batch normalization and a dropout regularization of 0.2. So the final layer has 206 units, which correspond to the 206 mechanism of actions. And therefore, these are all passed through sigmoid activation because I want to know if those mechanism of actions are present or not. Now, then these are trained over these 28,000 drug molecules, and a stochastic gradient descent is performed for optimization of the weights, and the loss function is a cross entropy loss function. So the network parameters are as follows for the deep learning architecture. So the total number of parameters are 2012, 686. And the trainable parameters are 2011, 662, because 1024 correspond to batch normalization. So the around 24,000 data points are shuffled. Those correspond to the various drugs. And they're divided into 70% training, 20% validation, and 10% test data. So the final slide gives you the network performance. Like I said, I have a binary cross entropy loss function. The training batch size is 32. I do Javier initialization of the weights. The learning rate is 1e minus 4. And for optimization, I use adaptive moment estimation, which means the weights can learn individually. Then a plot here shows for both the training and the validation that the loss decreases in about 10 iterations to very close to 0. And the binary accuracy increases for both the training and the validation, also very close to +1. So once that is performed, I do the test computation. So the test data is something that the deep learning has never seen. And it reports a loss of 0.016 and accuracy of 0.997, which means that if you take a new drug, a novel drug, and then apply it to these 100 cells, and then note the cell viabilities and the gene expressions, then this deep learning model is going to estimate with a very high accuracy the possible mechanism of action for this new drug. Thank you.